So transfer function, so symbolized as h of omega. This is the um, ratio of the output from a linear network divided by the input to that linear network. So since the output is the output and the input are both phasors, so that makes the transfer function a phasor as well. So therefore the transfer function must have both a magnitude and a phase. So transfer functions can be a ratio of an output voltage and an input voltage. So we call that transfer function a voltage gain. Now, if it is a ratio of two currents, we call that a current gain. It's possible for the transfer function to be a ratio of a voltage and a current. So in that case, the transfer function will have a dimension of ohms. On the other hand, if it is a ratio of a current over a voltage, it will have a dimension of an admittance, so that will be a Siemens. So how do we relate frequency response to the transfer function? So frequency response is simply um, obtained by plotting the a variation of the magnitude and the phase of the transfer function against any variation in the frequency. So let's apply this to a specific example. So let's say we have an RL circuit, a series RL circuit, and let's say we take our output across the inductor. So this circuit is stimulated by a sinusoidal function, v sub s equals Pm cosine omega t. So let's obtain the transfer function V naught over Vs. So where V naught again is the voltage across the inductor. So V sub O over V sub I. So V sub O can be obtained using voltage division. So this is V sub naught. So all over V sub S. So we have V sub S cancel and we have this final result. So the transfer function is really a phasor. So we can obtain the magnitude of the phasor, and so this is the magnitude. So to get the magnitude, we simply convert the the numerator and denominator to its equivalent polar form and manipulate the magnitudes. Okay, so this is the magnitude of the numerator. This is the magnitude of the denominator. So simplifying this, you will get something like this, where omega naught is defined as R over L. We can do the same for the phase. So for the phase, we simply get the phase angle of the um, polar equivalent of the numerator and the denominator. So you will have 90 degrees minus the angle in the denominator. And simplifying this, you will get inverse tangent R over omega L, which simplifies to inverse tangent omega naught over omega. And then after getting the magnitude and the phase, we plot it against uh, the variation in omega of the input voltage. So as you can see, the plot reveals that the magnitude varies from 0 for omega equals 0 and it increases to unity as omega increases. Specifically, we have the value of the magnitude at omega equals omega naught, which is around 0.707. Now, for the phase angle, it varies from maximum value of 90 degrees, and it decreases as omega increases. And likewise, at omega equals omega naught, we have the value of the phase angle equals 45 degrees. On the next video, we'll have another example.